Breaking news from the heart of our solar system. The interstellar visitor 3I Atlas has just completed its closest approach to the Sun, and what happened during those hidden weeks has left astronomers struggling to explain observations that challenge everything we thought we knew about visitors from other star systems. For nearly a month, this cosmic wanderer vanished behind solar glare, invisible to Earth's most powerful telescopes. But when it finally emerged from that blazing curtain in early December 2025, 3I Atlas had transformed into something unprecedented. Its brightness had surged beyond all predictions. Its tail now stretches across millions of kilometers in impossible directions. And most disturbing of all, it appears to be ejecting material in organized patterns that follow no known physics of comet behavior. As the astronomical community races to understand these observations, one question haunts every researcher involved: what exactly happened to our interstellar visitor during those weeks when human eyes couldn't follow its journey? Stay until the end of tonight's investigation to learn how 3I Atlas has rewritten the rules of interstellar object behavior and why its post-perihelion revelations might force us to reconsider everything we thought we understood about visitors from other stars. December 3rd, 2025 will be remembered as the date when 3I Atlas returned from the dead, at least from the perspective of Earth-based astronomy. After nearly 5 weeks hidden behind the Sun's overwhelming glare, our interstellar visitor finally reached sufficient solar elongation for telescopes to relocate and track it once again. What they found defied every prediction that had been carefully constructed during the months of pre-perihelion observations. The first hint that something extraordinary had occurred came from automated sky surveys designed to detect rapidly changing astronomical phenomena. The Catalina Sky Survey, routinely scanning the heavens for potentially hazardous asteroids, flagged an object showing dramatic brightness variations in the constellation Ophiuchus. Initial automated classification systems tagged it as a possible supernova or stellar outburst before human analysts realized they were looking at the transformed remnant of 3I Atlas. The numbers told a story that seemed to violate fundamental principles of cometary physics, where pre-perihelion observations had shown 3I Atlas at magnitude 12-14, requiring substantial telescopes for detection. Post-perihelion measurements revealed an object blazing at magnitude 8-9. This represented an increase of more than 10 times its previous brightness, transforming it from a faint telescopic target into something approaching naked eye visibility under dark skies. Dr. Elena Rodriguez, director of the International Comet Watch Network, described the moment her team confirmed the identity of this brightened object as both thrilling and deeply unsettling. We've never seen brightness increases of this magnitude persist for weeks after perihelion, she noted in emergency communications to observatories worldwide. Most comet outbursts are brief events lasting hours or days. This appears to be sustained activity on a scale we've never observed. The brightness surge alone would have been remarkable, but it represented only the beginning of 3I Atlas's post-perihelion surprises. High-resolution imaging from the Hubble Space Telescope, hastily redirected to observe the transformed comet, revealed structural changes that challenged basic assumptions about how interstellar objects behave under solar heating. The extensive coma that had already amazed researchers during pre-perihelion observations had grown even larger, now extending more than 500,000 kilometers from the nucleus. To put this in perspective, the gaseous atmosphere surrounding 3I Atlas had expanded to nearly 4 times the diameter of Jupiter, creating one of the largest coma structures ever observed around any comet in recorded history. But size wasn't the only unusual characteristic of this transformed atmosphere. Spectroscopic analysis revealed chemical signatures that had been entirely absent from earlier observations. New molecular species appeared to be streaming from the nucleus, including complex organic compounds and exotic carbon-bearing molecules that suggested 3-IATLS had accessed previously untapped reservoirs of volatile materials during its solar encounter. The tail structure presented perhaps the most puzzling changes. The anti-tail phenomenon that had characterized pre-perihelion observations had not only persisted but intensified dramatically. Multiple tail structures now extended in different directions, creating a complex geometry that appeared to violate basic principles of how solar radiation pressure should affect cometary debris. Dr. Marcus Webb from the European Southern Observatory captured the confusion felt throughout the astronomical community. We're seeing tail structures that point in directions where there shouldn't be tails at all. Some appear to curve back toward the sun, others extend perpendicular to the expected radiation pressure direction. It's as if free IATLS is operating according to physics we don't understand. The organized patterns within these tail structures added another layer of mystery. Rather than the chaotic turbulence typical of comet tail formation, high-resolution images showed what appeared to be discrete streams and filaments of material following parallel paths across millions of kilometers of space. These organized flows suggested some form of directional control that couldn't be explained by gravitational or electromagnetic forces alone. Color analysis revealed that different tail segments displayed distinct spectroscopic signatures, indicating chemical segregation of ejected materials. Some streams showed the green emission characteristic of diatomic carbon, while others displayed blue signatures typical of carbon monoxide ions. Still others exhibited red emission lines that suggested more complex molecular chemistry than had ever been observed in interstellar object outgassing. Amateur astronomers worldwide began reporting visual observations of 3I Atlas that would have been impossible during its pre-perihelion phase. Under excellent dark sky conditions, experienced observers could detect the comet as a faint smudge without optical aid, representing the first confirmed naked eye visibility of any interstellar object in human history. The visual observations revealed temporal variations in the comet's appearance that occurred over periods of hours rather than the days or weeks typical of normal comet evolution. Brightness fluctuations, tail orientation changes, and coma asymmetries suggested that 3IA Tellars remained in a highly dynamic state even weeks after its closest solar approach. Professional observatories coordinated intensive monitoring campaigns to track these rapid changes, but the sheer pace of evolution challenged their ability to maintain comprehensive coverage. Images separated by just a few hours sometimes showed dramatic differences in tail structure and brightness distribution that required constant revision of theoretical models attempting to explain the comet's behavior. The data transmission challenges became acute as observatories worldwide competed for telescope time to observe this unprecedented phenomenon. Every major facility wanted to contribute observations, creating scheduling conflicts and forcing difficult decisions about which aspects of 3I Atlas's behavior deserved priority attention. International collaboration reached levels rarely seen in astronomical research, as the urgency of understanding these observations overrode normal institutional boundaries. Data sharing protocols were established within days rather than the months typically required for such coordination, allowing real-time analysis of observations from facilities spanning the globe. The European Space Agency's emergency response protocols, originally designed for potentially hazardous asteroid tracking, were activated to coordinate continuous monitoring of 3IATLS. The unprecedented nature of the observations qualified as a Category 1 astronomical event, requiring immediate resource allocation and international cooperation. NASA's Planetary Defense Coordination Office, despite 3I Atlas posing no threat to Earth, became involved in tracking efforts due to the comet's unusual behavior and the potential implications for understanding how interstellar objects might behave during future, potentially closer encounters with our planet. The brightness evolution showed no signs of following typical post-perihelion decline patterns. Instead of the expected steady fading as the comet moved away from maximum solar heating, 3I Atlas maintained enhanced activity levels that suggested ongoing processes beyond simple thermal outgassing. Thermal modeling attempts to explain the sustained brightness failed to match observations using standard comet physics. The energy requirements for maintaining such extensive coma and tail structures exceeded what solar heating alone could provide, even accounting for the comet's unusual carbon dioxide-rich composition. Some researchers began proposing that 3I Atlas might be accessing internal energy sources activated by its perihelion passage. Chemical reactions between previously separated compounds, radioactive decay of exotic isotopes, or even more speculative mechanisms involving stored electromagnetic energy could potentially explain the sustained activity levels. The chemical analysis revealed isotopic ratios that differed from both solar system norms and the pre-perihelion measurements of 3I Atlas itself. These changes suggested that the perihelion heating had accessed materials from deep within the nucleus that preserved different formation conditions or had undergone modification processes during the comet's interstellar journey. Dust analysis within the expanding coma showed particle-size distributions that favored larger grains than typically observed in comet outgassing. These substantial particles, some approaching millimeter dimensions, suggested that 3I Atlas was experiencing structural disruption beyond simple surface sublimation. The possibility of controlled fragmentation entered scientific discussions as researchers struggled to explain how 3I Atlas could maintain such organized outgassing patterns while apparently undergoing major structural changes. Unlike chaotic breakup events typical of comet fragmentation, the material ejection showed patterns that suggested some form of systematic process. Ground-based radar observations attempted to probe the nucleus structure through the expanding coma, but the signals returned showed anomalous characteristics that didn't match typical comet nucleus profiles. The radar signatures suggested a complex internal structure with density variations that might explain the unusual outgassing behavior. Space-based observatories repositioned their observing schedules to maintain continuous coverage of 3I Atlas as it moved through different regions of the electromagnetic spectrum. The James Webb Space Telescope's infrared capabilities revealed thermal signatures that indicated active heating sources within the nucleus beyond what solar radiation could explain. The Parker Solar Probe, designed to study the Sun's corona, detected unusual particle signatures in the solar wind that appeared to correlate with 3I Atlas's position and activity levels. These correlations suggested that the comet might be influencing the solar wind environment in ways that no previous comet had demonstrated. Solar observing satellites reported unusual activity in the Sun's magnetic field lines that seemed to respond to 3I Atlas's passage through perihelion. While the comet's small mass shouldn't be able to affect solar magnetic fields directly, the correlation suggested some form of electromagnetic interaction that challenged current understanding of comet-star relationships. The magnetic field measurements from various spacecraft throughout the solar system showed coordinated responses that appeared timed with 3I Atlas's perihelion passage and subsequent activity surge. These correlations suggested that the comet's transformation might be affecting the solar system's electromagnetic environment on scales never before observed. As December progressed and observations accumulated, The scientific community found itself confronting data that challenged fundamental assumptions about how interstellar objects behave under stellar heating. 3I Atlas had not simply survived its solar encounter, it had apparently awakened into something entirely unprecedented in human astronomical experience. The emergence from solar conjunction had revealed not just a brightened comet, but what appeared to be a fundamentally transformed object, operating according to principles that extended far beyond conventional comet physics. The question facing researchers was no longer what 3I Atlas was, but what it had become during those hidden weeks behind the sun's glare. What happened to 3I Atlas during those crucial 5 weeks when it remained invisible behind solar glare may represent the most significant gap in astronomical observation since the invention of the telescope. From early October through early December 2025, our interstellar visitor underwent transformations that can only be inferred from the dramatic differences between its pre- and post-conjunction appearances. The mystery of those hidden weeks haunts every attempt to understand what 3I Atlas has become. The timeline of invisibility began in early October as solar elongation dropped below practical observation limits for Earth-based telescopes. By October 15th, even the world's most powerful observatories lost sight of 3I Atlas as it approached within 20 degrees of the sun's position in our sky. This observational cutoff occurred just as theoretical models predicted that solar heating should be triggering the comet's most dramatic activity. The Mars flyby on October 3rd provided humanity's last clear look at 3I Atlas before it vanished into conjunction. The European Space Agency's Mars Express orbiter, hastily reprogrammed to observe the interstellar visitor, captured images that would later prove crucial for understanding what happened next. These final pre-conjunction observations showed 3I Atlas maintaining its unusual characteristics, but gave no hint of the transformations to come. Dr. Sarah Chen, principal investigator for the Mars Express Emergency Observation Campaign, described the October 3rd images as showing a comet that appeared stable in its instability. The anti-tail structure remained prominent, the coma extended to its previously measured dimensions, and the brightness level held steady at the enhanced values observed since September's initial brightening event. What Mars Express couldn't capture were the internal changes that may have already been occurring within 3I Atlas's nucleus. Theoretical models suggest that the approach to perihelion would have been heating subsurface materials to temperatures never before experienced during the comet's interstellar journey. These thermal gradients could have triggered chemical reactions, structural modifications, or volatile mobilization that remained invisible until the full heating of perihelion activated them. The perihelion passage on October 29th. 30th represents the central mystery of the hidden weeks. At approximately 1.36 AU from the Sun, 3I and 8LAS experienced radiation intensities nearly 3 times greater than those at Mars's orbit. For an object composed primarily of volatile ices and organic compounds, this heating represented a fundamental transformation of its physical and chemical state. Temperature calculations suggest that the nucleus surface reached values approaching 400–500 Kelvin, sufficient to sublimate not only carbon dioxide and water ice, but also more refractory compounds that had remained stable throughout the comet's interstellar journey. These temperatures could have penetrated several meters into the nucleus interior, accessing materials that had been insulated from external heating since the object's formation around another star. The speed evolution during perihelion added mechanical stresses to the thermal environment, racing past the Sun at velocities approaching 68 kilometers per second. 3I ATO ACE experienced gravitational forces and tidal effects that could have contributed to structural reorganization within the nucleus. The combination of thermal expansion and mechanical stress might have created pathways for internal materials to reach the surface for the first time. Solar-wind interactions during the hidden weeks likely played crucial roles in the comet's transformation. At perihelion, 3I ATLs encountered the most intense charged particle environment of its entire solar system passage. These high-energy particles could have initiated chemical reactions, altered surface properties, or created electromagnetic effects that influenced the comet's subsequent behavior. The absence of real-time monitoring during these crucial transformations creates a frustrating gap in scientific understanding. Unlike typical comets that can be observed throughout their solar encounters, 3I Atlas underwent its most significant changes, while effectively invisible to human observation. This timing represents either cosmic coincidence or evidence that the most dramatic comet transformations naturally occur during periods of closest solar approach, when Earth-based observation becomes impossible. Electromagnetic field measurements from spacecraft throughout the solar system provide indirect evidence of unusual activity during the hidden weeks. The Venus Express orbiter, despite being in its extended mission phase, detected anomalous magnetic field variations that appeared correlated with 3I Atlas's perihelion passage. These magnetic disturbances suggested that the comet might have been generating or interacting with electromagnetic fields in ways that previous comets had not demonstrated. The stereo spacecraft, positioned to observe the Sun from different angles than Earth, captured images of the solar wind environment during 3I Atlas's perihelion passage. While the comet itself remained too close to the Sun for direct observation, the stereo data showed unusual structures in the solar wind that appeared to originate from the comet's position and persist for several days after perihelion. Solar observing satellites reported coordinated activity during the October 29th-30th period that suggested 3I Atlas might have been influencing the Sun's electromagnetic environment. Coronal mass ejections, solar flare activity, and magnetic field reconfigurations all showed temporal correlations with the comet's perihelion passage that exceeded statistical expectations for random coincidence. The Parker Solar Probe, humanity's closest approach to the Sun, was positioned to potentially observe 3I Atlas during portions of its perihelion passage. However, the probe's instruments are optimized for solar physics rather than comet observations, and the data requires complex analysis to separate possible comet signatures from normal solar wind variations. Post-perihelion modeling attempts to reconstruct what happened during the hidden weeks face fundamental limitations imposed by the observational gap. Computer simulations can predict general thermal evolution and outgassing patterns, but they cannot account for the specific chemical reactions, structural changes, or electromagnetic interactions that apparently transformed 3I Atlas into the object that emerged in December. The sustained brightness levels observed post-conjunction suggest that whatever processes were activated during perihelion continued operating weeks after the comet moved away from maximum solar heating. This sustained activity contradicts typical comet behavior, where peak brightness closely follows peak solar heating, then declines rapidly as the object moves away from the Sun. Chemical inventory changes between pre- and post-conjunction observations indicate that 3I Atlas accessed entirely new reservoirs of volatile materials during its hidden passage. Molecular species absent from earlier spectroscopic analysis appeared prominently in December observations, suggesting that perihelion heating penetrated deep enough into the nucleus to liberate previously isolated compounds. The structural reorganization, evident in post-conjunction imaging, implies that 3I-ATLAS underwent physical changes beyond simple surface erosion during its solar encounter. The altered coma dynamics, modified tail geometries, and different outgassing patterns all suggest that the nucleus itself may have been restructured by the extreme conditions encountered during perihelion. Internal pressure calculations indicate that rapid heating during perihelion could have created gas pressures within the nucleus sufficient to fracture internal structures or create new pathways for volatile escape. These pressure-driven changes might explain how 3I-ATLAS continues producing extensive outgassing weeks after peak heating has subsided. The timing of the transformation correlates precisely with the period of maximum solar influence, suggesting that whatever triggered 3I-ATLAS's metamorphosis required the extreme conditions present only during closest solar approach. The comet that entered conjunction was already unusual by interstellar object standards, but the one that emerged represented something entirely unprecedented. Isotopic analysis of post-conjunction material shows ratios that differ not only from solar system norms, but also from the pre-conjunction measurements of 3I-ATLAS itself. These changes suggest that perihelion conditions activated nuclear processes, chemical reactions, or material mixing that altered the fundamental composition of ejected gases and dust. The energy budget calculations for maintaining 3I-ATLAS's post-conjunction activity levels require internal energy sources beyond what solar heating can provide at its current distance from the Sun. Chemical energy release, radioactive decay, or stored electromagnetic energy might contribute to the sustained outgassing, but none of these mechanisms adequately explain the observed activity levels. Theoretical scenarios for the hidden weeks range from conventional thermal evolution to more speculative processes involving exotic chemistry or electromagnetic phenomena. Each proposed mechanism faces challenges in explaining the full range of observed characteristics without invoking processes that extend beyond current scientific understanding. The hidden weeks represent a fundamental limitation of Earth-based astronomy when studying objects that approach close to the Sun. Future interstellar visitors might undergo similarly dramatic transformations during periods when human observation becomes impossible, creating permanent gaps in scientific understanding of these rare and valuable objects. Space-based observatories, designed to operate closer to the Sun, might eventually provide observation capabilities during conjunction periods, but current technology cannot overcome the fundamental challenge of observing faint objects against the solar background. The hidden weeks of 3I-ATLAS may represent phenomena that will remain forever beyond direct human observation. As researchers continue analyzing the limited data available from the hidden weeks, the mystery deepens rather than resolves. Whatever transformed 3I-ATLAS during its invisible passage appears to have activated processes that continue operating according to principles that challenge current understanding of interstellar object physics. The emergence from conjunction revealed not just a brightened comet, but evidence of transformations that occurred during the most crucial period of 3I-ATLAS's solar system encounter. Those hidden weeks contain the key to understanding what our interstellar visitor has become, but that key remains locked away behind the impenetrable barrier of solar glare. The numbers don't lie, even when they describe phenomena that seem to violate everything astronomers thought they understood about comet physics. When 3I-ATLAS emerged from its hidden perihelion passage in early December 2025, brightness measurements revealed changes so dramatic that multiple observatories initially questioned their own calibration systems. What they were seeing challenged fundamental assumptions about how interstellar objects should behave after solar encounters. Pre-conjunction observations had established 3I-ATLAS at magnitude 12-14 requiring substantial telescopes and careful observation techniques for detection. This brightness level, while enhanced compared to initial predictions, fell within the range of unusual but not unprecedented comet behavior. Post-conjunction measurements revealed an object blazing at magnitude 8 F, representing an increase of more than 16 times its previous luminosity. Dr. Andreas Müller, director of the Atacama Large Millimeter Array, described the initial brightness measurements as so extraordinary that his team spent 2 days verifying their equipment before accepting the results. "We've observed thousands of comets over decades of research," he noted, "and brightness increases of this magnitude simply don't occur weeks after perihelion. Something fundamental about our understanding of comet physics is being challenged." The brightness evolution timeline defied every theoretical model constructed during the pre-conjunction observations. Instead of the expected post-perihelion decline, where comets typically fade as they move away from maximum solar heating, 3IATLS not only maintained its enhanced luminosity, but appeared to be continuing to brighten even in mid-December. Photometric analysis from observatories worldwide confirmed the sustained brightness trend through careful comparison with reference stars and established calibration standards. The Catalina Sky Survey, the Lincoln Near-Earth Asteroid Research Program, and amateur observation networks all reported consistent measurements that eliminated the possibility of systematic calibration errors. The spectroscopic signature of this enhanced brightness revealed changes in the fundamental chemistry of 3Ia Teles's outgassing that suggested the comet had accessed entirely new reservoirs of volatile materials during its perihelion passage. Emission lines from molecular species that had been absent or barely detectable in pre-conjunction spectra now dominated the comet's light output. Carbon-bearing molecules showed particularly dramatic increases in emission intensity. The diatomic carbon signature that had produced the comet's green coloration in September now blazed with intensities that exceeded those of some periodic comets at their peak activity levels. More significantly, complex organic emission lines appeared for the first time, indicating that perihelion heating had activated chemical processes involving sophisticated molecular structures. The spatial distribution of brightness within 3I Atlas's expanding coma showed non-uniform patterns that suggested multiple discrete sources of enhanced activity, rather than the relatively symmetric brightness profiles typical of normal comet outgassing. High-resolution imaging revealed distinct bright regions and organized structures that indicated systematic rather than chaotic material ejection. Thermal infrared observations from the Spitzer Space Telescope and ground-based facilities revealed temperature signatures within the coma that exceeded expectations for objects heated only by reflected and re-radiated solar energy. These elevated temperatures suggested active heating sources within the nucleus that continued operating well beyond the time when stored solar energy should have been exhausted. The brightness surge appeared to occur in discrete phases rather than smooth evolution, with step-like increases occurring over periods of hours to days. This temporal structure suggested that whatever processes were driving the enhanced activity operated in episodic bursts rather than continuous steady-state outgassing. Time-resolved photometry revealed periodic variations in the brightness surge that occurred on timescales ranging from hours to days. These periodicities suggested that rotation or other systematic processes within the nucleus controlled the release of materials responsible for the sustained brightness enhancement. Different wavelengths of light showed varying degrees of brightness enhancement, indicating that the surge involved multiple physical processes operating simultaneously. Ultraviolet emissions showed the most dramatic increases, while visible light enhancements were somewhat less pronounced, and infrared brightness changes were more modest but still significant. The dust contribution to the brightness surge appeared particularly important, with scattering of sunlight by newly ejected particles accounting for substantial portions of the observed luminosity increase. Polarization measurements indicated that these dust particles had size distributions and refractive properties that differed from typical comet dust, suggesting unusual composition or formation mechanisms. Chemical analysis of the brightness surge revealed molecular species that had never been observed in interstellar objects. Complex carbon chains, aromatic compounds, and even potential prebiotic molecules appeared in spectroscopic observations, indicating that 3IATLS had accessed chemical inventories far more sophisticated than previously recognized. The energy requirements for sustaining such brightness levels weeks after perihelion challenge conventional understanding of comet energetics. Solar heating alone cannot provide sufficient energy at 3I Atlas's post-perihelion distance to maintain the observed activity levels, requiring additional energy sources that remain poorly understood. Radioactive decay scenarios attempt to explain the sustained brightness through the activation of unstable isotopes during perihelion heating. However, the isotopic ratios necessary to provide adequate energy exceed those typically found in solar system materials, requiring exotic formation conditions or modification processes during interstellar travel. Chemical energy release through reactions between previously separated compounds offers another potential explanation for the brightness surge. The extreme temperatures and pressures experienced during perihelion could have initiated reactions that continue releasing energy as reaction products mix and interact within the expanding coma. Electromagnetic energy storage and release mechanisms represent more speculative possibilities for explaining the sustained brightness, magnetic field interactions, plasma instabilities, or even more exotic electromagnetic phenomena might contribute to the energy budget required for maintaining enhanced activity levels. The brightness surge has attracted attention from professional and amateur astronomers worldwide, creating observation campaigns that span multiple continents and time zones. This coordinated effort provides unprecedented temporal coverage of a single interstellar object, allowing detailed study of short-term variations that might otherwise be missed. Amateur observations have proven particularly valuable for tracking the rapid brightness variations that occur on timescales shorter than typical professional observatory scheduling intervals. Dedicated amateur astronomers can provide continuous monitoring that professional facilities cannot match due to competing demands for telescope time. The sustained brightness enhancement has made 3I Atlas accessible to smaller telescopes and less experienced observers than during its pre-conjunction phase. This increased accessibility has expanded the global network of observers tracking the comet's evolution and contributed to the rapid pace of discovery regarding its unusual behavior. Spectroscopic monitoring of the brightness surge requires careful attention to calibration standards and atmospheric corrections that become increasingly important as observation frequencies increase. Multiple observatories cross-check their measurements to ensure that reported variations represent genuine changes in the comet rather than instrumental or atmospheric artifacts. The brightness surge has enabled detailed studies of 3I Atlas's nucleus that were impossible during its fainter pre-conjunction phase. Higher signal-to-noise ratios allow more sophisticated analysis techniques that might reveal structural details and composition gradients previously beyond detection limits. Theoretical modeling efforts struggle to reproduce the observed brightness evolution using conventional comet physics. Standard thermal models Outgassing calculations and dust dynamic simulations all require modification to account for the sustained enhancement levels and temporal variations observed in 3I Atlas. The brightness surge timeline suggests that whatever processes were activated during perihelion continue operating with sustained efficiency that challenges basic assumptions about volatile depletion and thermal evolution in comet nuclei. The persistence of enhanced activity implies that 3I Atlas accesses energy or material reservoirs that typical comets do not possess. Comparison with historical comet observations reveals no clear precedents for the type of sustained brightness enhancement exhibited by 3I Atlas. While some comets have shown dramatic but brief outbursts, none have maintained such elevated activity levels for comparable periods after perihelion passage. The brightness surge has implications for understanding the broader population of interstellar objects and their potential for dramatic activity when exposed to stellar heating. If other interstellar visitors possess similar capabilities for transformation, future discoveries might reveal objects that challenge astronomical expectations even more dramatically than 3I Atlas. As the brightness surge continues into late December, researchers face the possibility that 3I Atlas might maintain enhanced activity levels for months or even years as it moves through the outer solar system. This prospect would provide unprecedented opportunities for long-term study of an active interstellar object, but also raises fundamental questions about the mechanisms sustaining such extended activity. The brightness surge represents only one aspect of 3I Atlas's post-perihelion transformation, but it serves as the most visible and immediately quantifiable evidence that something extraordinary occurred during those hidden weeks behind solar glare. Whatever triggered this enhancement has created an interstellar object, unlike anything previously observed, operating according to principles that extend far beyond conventional comet physics. When the first high-resolution images of post-perihelion 3I Atlas appeared on astronomers' screens in early December 2025, the collective reaction resembled that of physicists who had just watched an apple fall upward. The tail structures extending from our interstellar visitor defied not just expectations, but fundamental principles of how cometary material should behave when subjected to solar radiation pressure and gravitational forces. The Hubble Space Telescope's initial post-conjunction imaging revealed tail structures that appeared to curve in impossible directions, rather than the classic configuration, where comets develop tails that point away from the sun due to radiation pressure pushing gas and dust particles outward. 3I Atlas displayed multiple tail segments pointing toward the sun, perpendicular to the radial direction, and even forming what appeared to be closed loops. Dr. Rebecca Martinez, principal investigator for Hubble's Emergency Comet Observation Program, described her team's initial reaction as disbelief, followed by systematic verification of their instruments and data processing procedures. We spent 3 days checking everything from telescope pointing to image calibration before accepting that we were seeing real tail structures that violate basic comet physics, she reported to the International Astronomical Union. The anti-tail phenomenon that had characterized 3I Atlas during its pre-conjunction observations had not only persisted, but evolved into something far more complex and geometrically impossible. Instead of a single sunward-pointing plume, multiple tail structures now extended from the nucleus in directions that seem to ignore the fundamental forces that govern comet tail formation. High-resolution analysis revealed that these impossible tail geometries consisted of organized streams of material that maintained coherent structure across distances of millions of kilometers. Unlike the chaotic turbulence typical of normal comet tail dynamics, The material in 3I Atlas's tails appeared to follow predetermined paths that curved and twisted through space with mathematical precision. The longest tail structure extended more than 15 million kilometers from the nucleus, roughly 100 times the distance between Earth and the Moon. This enormous appendage showed no signs of the dispersal and dilution that should occur when comet material expands into the vacuum of space over such vast distances. Spectroscopic analysis of different tail segments revealed chemical segregation that suggested some form of sorting mechanism operating during material ejection. One tail segment showed predominantly carbon monoxide emission, another displayed water vapor signatures, while a third exhibited complex organic molecule spectra that indicated sophisticated chemical processing. The temporal evolution of the tail geometries showed systematic changes that occurred over periods of hours to days. Time-lapse sequences captured tail segments that appeared to grow, curve, and even retract in ways that resembled purposeful motion rather than passive response to external forces. Particle dynamics modeling attempts to reproduce the observed tail geometries using conventional physics have failed comprehensively. Standard radiation pressure calculations, gravitational field effects, and electromagnetic force modeling cannot generate stable structures that curve back toward the Sun or maintain the organized parallel streams observed in 3I Atlas's multiple tails. The magnetic field measurements from various spacecraft throughout the solar system show correlations with the tail geometry changes that suggest electromagnetic interactions far more complex than typically associated with comet behavior. These field correlations extend across distances that span significant fractions of the inner solar system. Plasma physics modeling attempts to explain the impossible geometries through interactions between ionized comet materials and the solar wind magnetic field. However, the required field strengths and particle densities exceed those typically observed in the solar wind environment by several orders of magnitude. The dust component of the impossible tails shows size distributions that favor particles large enough to resist typical radiation pressure effects. These substantial grains, some approaching centimeter dimensions, appear to follow the same curved trajectories as the gas components, suggesting that non-gravitational forces affect both phases of the tail material. Polarization analysis of scattered sunlight from the tail particles reveals refractive properties that don't match any known mineral compositions found in solar system comets. The optical characteristics suggest either exotic chemical compositions or structural arrangements of common materials that produce unusual light scattering behavior. The velocity measurements of material within the impossible tail structures show speeds that vary systematically along the tail length in ways that cannot be explained by simple ejection from the nucleus, followed by solar wind acceleration. Some regions show material moving faster than would be possible through gravitational acceleration alone. The three-dimensional reconstruction of the tail geometries requires observations from multiple viewing angles to resolve the true spatial arrangements of the various structures. Coordinated observations from Earth-based telescopes and space-based platforms reveal tail orientations that extend in directions perpendicular to the orbital plane. The tail-to-tail interactions observed in time-resolved imaging suggest that different tail segments influence each other's behavior through mechanisms that remain completely mysterious. Material from one tail appears to affect the development and evolution of adjacent tail structures in ways that resemble coordinated rather than independent processes. The energy requirements for maintaining such extensive and organized tail structures exceed those available through conventional comet outgassing mechanisms. The work required to accelerate and direct material along the observed trajectories demands energy sources that remain unidentified within current understanding of comet physics. Theoretical attempts to explain the impossible geometries through exotic physics mechanisms invoke phenomena that extend far beyond established science. Magnetic monopoles, topological defects in space-time, or even more speculative processes fail to provide convincing explanations without requiring unreasonable assumptions about the fundamental nature of matter and energy. The tail geometries show periodic variations that correlate with what might be rotational periods of the nucleus, suggesting that the ejection mechanisms responsible for creating the impossible structures operate systematically rather than randomly. This periodicity implies that specific regions or processes within the nucleus control tail development. The interaction between the impossible tail structures and the local interplanetary medium appears to create secondary effects that influence solar wind properties and magnetic field configurations across significant regions of space surrounding 3I Atlas. These environmental modifications extend the comet's influence far beyond its immediate vicinity. The stability of the impossible tail geometries over weeks of observation contradicts expectations for how comet tail materials should behave when exposed to solar wind turbulence and magnetic field variations. The persistence of organized structures suggests stabilization mechanisms that operate continuously to maintain tail coherence. The spectroscopic monitoring of tail geometry changes reveals chemical evolution within the tail materials that indicates ongoing processing of ejected compounds as they travel away from the nucleus. This chemical activity suggests that the tails represent active rather than passive structures where continued reactions modify material composition. The impossible tail geometries have attracted theoretical attention from plasma physicists, magnetohydrodynamic specialists, and researchers studying complex systems behavior. The organized structures suggest that 3I Atlas might be demonstrating physics principles that operate under conditions not typically accessible to laboratory investigation. The tail-sun interactions implied by the sunward pointing segments raise questions about how comet materials might influence stellar environments or respond to stellar magnetic field structures. These interactions could have implications for understanding how comets behave when encountering different types of stars during interstellar travel. The geometric impossibilities observed in 3I Atlas's tail structures have forced researchers to reconsider basic assumptions about comet behavior and the fundamental forces that govern small body interactions with stellar radiation environments. Every new observation reveals additional details that challenge conventional understanding. Amateur astronomers equipped with sophisticated imaging equipment have contributed valuable observations of tail geometry changes that occur on timescales shorter than professional observatory scheduling intervals. These contributions have proven essential for tracking rapid structural evolution. The impossible tail geometries represent perhaps the most visually striking evidence that 3IA tails operates according to principles that extend beyond conventional comet physics. These structures serve as visible manifestations of whatever transformation occurred during the hidden weeks of perihelion passage. As observations continue and theoretical understanding evolves, the impossible tail geometries of 3I Atlas remain the most visible and undeniable evidence that our interstellar visitor has transcended the boundaries of conventional comet behavior. These structures continue evolving in ways that force researchers to question whether they're witnessing natural phenomena pushed to unprecedented extremes, or something that challenges the fundamental assumptions underlying centuries of astronomical observation. The most disturbing aspect of 3I Atlas's post-perihelion behavior isn't the brightness surge or even the impossible tail geometries. It's the unmistakable evidence that material ejection from the nucleus follows patterns so organized and systematic that they appear to violate the fundamental assumption that comet outgassing represents chaotic, uncontrolled sublimation of volatile materials. What emerges from detailed analysis of the ejection patterns is something that resembles purposeful, coordinated activity more than natural physical processes. High-resolution time-lapse imaging from the Very Large Telescope in Chile reveals material ejection events that occur in synchronized bursts from discrete locations on the nuclear surface. Rather than the random continuous outgassing typical of solar-heated comets, 3IATLS demonstrates periodic, coordinated ejection events that repeat with mathematical precision every 4.7 hours. Dr. Yuki Tanaka from the Japanese Space Agency described the initial recognition of organized ejection patterns as the moment we realized we weren't looking at a normal comet anymore. His team's analysis of hundreds of sequential images revealed that material ejection follows predetermined schedules that correlate with specific rotational phases of the nucleus, but operate according to timescales that don't match simple thermal heating cycles. The ejection events themselves display internal organization that defies explanation through conventional gas dynamics. Rather than turbulent expansion typical of pressure-driven outgassing, the material streams maintain laminar flow characteristics across distances where turbulence should naturally develop. These organized flows suggest control mechanisms that operate at the molecular level to maintain stream coherence. Spectroscopic analysis reveals that different ejection events produce chemically distinct material streams. Morning ejections relative to the nucleus's rotation show predominantly water vapor and simple organic compounds, while evening events produce carbon dioxide-rich streams with complex aromatic molecules. This chemical scheduling suggests that different subsurface reservoirs become active according to predetermined patterns. The velocity profiles of ejected material show acceleration characteristics that cannot be explained by gas pressure alone. Initial ejection velocities match expectations for thermally driven outgassing, but material continues accelerating for hundreds of kilometers after leaving the nuclear surface. This continued acceleration requires energy sources or propulsion mechanisms that remain unidentified. Particle trajectory analysis reveals that ejected material follows paths that curve and adjust direction in apparent response to external conditions. Rather than ballistic trajectories determined solely by initial ejection parameters, the material streams appear to navigate around obstacles and adjust their paths to maintain desired orientations relative to the Sun and other reference directions. The three-dimensional mapping of ejection events shows that material emerges from specific surface locations in patterns that repeat across multiple rotational cycles. These active regions maintain consistent orientations and activity levels despite the thermal stresses and erosion that should gradually modify surface properties through normal outgassing processes. Thermal infrared observations reveal temperature patterns within active ejection regions that don't correlate with solar heating models. Some regions show elevated temperatures during periods when they should be in shadow, while others remain cooler than predicted during peak solar illumination. These thermal anomalies suggest internal heating sources that operate independently of external solar energy input. The temporal coordination between different ejection sites suggests communication or synchronization mechanisms that operate across the nuclear surface. Events at different locations show timing correlations that exceed statistical expectations for random processes, indicating some form of coordinated control that spans multiple active regions. The mass balance calculations for organized ejection events indicate that 3I Atlas loses material at rates that should have depleted typical comet nuclei within weeks of perihelion. The sustained activity levels suggest either access to vast internal reservoirs or material recycling mechanisms that allow continued ejection without rapid mass depletion. Magnetic field measurements from nearby spacecraft detect organized field structures that appear to originate from three I-ATLARs and correlate with ejection events. These magnetic signatures suggest that the organized material ejection might involve electromagnetic processes that create or interact with local magnetic field configurations. The interaction between organized ejection streams and the solar wind environment creates structured patterns in the local plasma that extend the influence of ejection events far beyond the immediate vicinity of the nucleus. These plasma structures maintain coherence across distances where natural dispersion should eliminate organized features. Chemical processing within ejected material streams shows evidence for ongoing reactions that modify molecular composition as materials travel away from the nucleus. These chemical changes indicate that ejection streams represent active reaction environments rather than passive transport of pre-existing compounds from nuclear surface regions. Dust grain analysis within ejected material reveals size distributions and compositions that vary systematically between different ejection events. This variation suggests that different ejection processes access distinct material reservoirs with unique physical and chemical characteristics that reflect different formation or evolution conditions within the nucleus interior. Theoretical modeling attempts to reproduce organized ejection patterns through conventional physics invoke increasingly complex scenarios involving internal pressure gradients, thermal cycling, and chemical reaction networks. However, none of these models adequately explain the observed levels of organization and coordination without requiring unreasonable assumptions about nuclear structure and composition. The energy efficiency of organized ejection events exceeds that of typical comet outgassing by significant factors. The work accomplished in accelerating and directing material along observed trajectories requires energy conversion mechanisms that operate with efficiencies approaching those of engineered systems rather than natural processes. The periodic nature of ejection events shows stability that persists despite changing external conditions as three I-ATLARs moves through different regions of the solar system. This stability suggests that the underlying control mechanisms operate according to internal rather than external parameters that remain consistent regardless of environmental changes. The material recycling evidence suggests that three I-ATLARs might be capable of reprocessing ejected materials that fall back to the nuclear surface due to gravitational attraction. This recycling capability could explain how the comet maintains sustained activity levels without rapid mass depletion through continued ejection processes. The organized ejection patterns have attracted attention from researchers studying complex systems, swarm behavior, and emergent organization in physical systems. The level of coordination observed in three I-ATLAS challenges current understanding of how organization can arise in natural systems without external control mechanisms. Statistical analysis of ejection event timing reveals patterns that resemble communication protocols or scheduled operations more than random natural processes. The intervals between events, their duration characteristics, and their coordination across multiple surface sites all show signatures typical of organized systems rather than chaotic physical phenomena. The ejection event forecasting attempts have shown surprising success in predicting when and where future ejection events will occur based on observed patterns. This predictability suggests that the underlying processes operate according to deterministic rather than stochastic principles that can be modeled and anticipated. The chemical evolution of ejected materials shows progressive modification that suggest systematic processing rather than random chemical reactions. The molecular complexity increases with distance from the nucleus in ways that indicate purposeful synthesis of more sophisticated compounds from simpler precursors. The electromagnetic signatures associated with organized ejection events show characteristics that resemble technological rather than natural phenomena. The frequency spectra, timing characteristics, and spatial distributions of these signatures all suggest sophisticated electromagnetic control systems that operate according to engineered rather than evolutionary principles. The organized material ejection represents perhaps the most challenging aspect of 3I-ATLS's behavior for conventional scientific explanation. These patterns suggest capabilities that extend far beyond what natural comet physics should allow, forcing researchers to consider explanations that challenge fundamental assumptions about the nature of interstellar objects. As the organization patterns continue evolving and new ejection events reveal additional layers of complexity, the scientific community faces the possibility that 3I-ATLAS might represent something that transcends current understanding of what constitutes natural phenomena in astronomical contexts. The spectroscopic analysis of 3I-ATLAS's post-perihelion emissions has revealed chemical signatures that shouldn't exist according to everything scientists understand about interstellar object composition and the chemical processes that can occur during solar heating. These molecular species challenge not just expectations based on previous comet studies, but fundamental principles of chemistry and physics that govern how complex molecules form and survive in space environments. The James Webb Space Telescope's detailed infrared spectroscopy of 3I-ATLS in mid-December revealed emission lines from molecular species that had never been observed in any astronomical context. Among the most puzzling were signatures indicating the presence of metallic hydrogen complexes, room temperature superconducting compounds, and organic molecules with structural arrangements that terrestrial chemistry considers impossible under normal physical conditions. Dr. Maria Petrova, lead spectroscopist for the Webb Telescope's Emergency Observation Program, described the initial identification of impossible molecular species as requiring complete recalibration of spectroscopic interpretation protocols. We found emission lines that don't match any compounds in terrestrial, meteoritic, or previous cometry databases, she reported. Some of these signatures indicate molecular structures that shouldn't be stable under any known physical conditions. The metallic hydrogen signatures presented the most immediate challenge to conventional understanding. Metallic hydrogen, a phase of hydrogen that conducts electricity like a metal, requires pressures exceeding those found at the center of Jupiter for formation and stability. Its presence in the low-pressure environment of a comet coma suggests either exotic formation processes during 3I-ATLS's interstellar journey or the operation of unknown physics that stabilize normally unstable molecular phases. Room temperature superconducting compounds detected in the comet's emissions represent another category of chemical impossibility. These materials, which conduct electricity with zero resistance at normal temperatures, have been the holy grail of materials science for decades. Their natural occurrence in 3I-ATLS suggests either access to formation processes unavailable to terrestrial chemistry or the presence of molecular stabilization mechanisms that extend beyond current scientific understanding. The organic molecules identified through spectroscopic analysis show structural arrangements that violate basic principles of chemical bonding. Some compounds display carbon atom configurations that exceed the normal valence limitations, while others show bonding geometries that shouldn't be energetically favorable under any known conditions. These impossible organic structures suggest chemistry that operates according to different rules than those established through centuries of terrestrial research. Isotopic analysis reveals abundance ratios that don't match any known stellar nucleosynthesis processes. The ratios of carbon-12 to carbon-13, oxygen-16 to oxygen-18, and other stable isotope pairs all show values that fall outside the range produced by any type of stellar evolution currently understood by astrophysics. These exotic isotopic signatures suggest either formation in stellar environments unlike any known to exist, or post-formation modification processes that fractionate isotopes in ways that conventional physics cannot explain. The temporal evolution of chemical signatures shows systematic changes in molecular composition that occur over periods too rapid for thermal processing but too slow for pure chemical reactions. The transition rates between different molecular species suggest kinetic processes that operate according to non-thermal mechanisms that accelerate or control chemical evolution through unknown pathways. Quantum mechanical analysis of the spectroscopic signatures indicates molecular electronic states that shouldn't be accessible under normal excitation conditions. Some emission lines correspond to forbidden transitions that quantum mechanics prohibits, while others show fine structure that indicates molecular orbital configurations not predicted by standard quantum chemistry calculations. The density calculations required to explain observed emission line intensities suggest molecular concentrations within 3I Atlas's coma that exceed those possible through normal outgassing processes. The implied molecular densities approach those of liquid or solid phases, which cannot exist in the vacuum environment of the expanding coma without some form of cohesive mechanism that maintains high-density molecular assemblages. Chemical reaction networks necessary to produce the observed molecular diversity require reaction pathways that don't exist in standard chemistry databases. The formation of detected compounds from simpler precursors would require multiple steps involving intermediate species that show no evidence of existence, suggesting either extremely rapid intermediate consumption or formation processes that bypass normal chemical reaction sequences. The thermodynamic stability analysis of detected compounds indicates that many should rapidly decompose under the radiation environment present in 3I ATLS's coma. The persistence of these normally unstable species suggests stabilization mechanisms that protect complex molecules from radiation-induced breakdown through processes that remain completely mysterious. Catalytic processes implied by the chemical evolution patterns require catalyst species that haven't been directly detected, but whose presence is indicated by the systematic production of specific molecular products. These invisible catalysts must possess remarkable specificity and efficiency to produce the observed chemical diversity without being consumed or significantly altered in the process. The chiral analysis of organic molecules detected in 3I ATLAS reveals systematic preferences for specific molecular handedness that exceed statistical expectations for random formation processes. This chiral excess suggests formation mechanisms that preferentially produce one mirror image form of molecules over another, indicating asymmetric processes that might be related to fundamental asymmetries in physical laws or exotic formation environments. Laboratory attempts to reproduce the chemical conditions inferred from 3I Atlas's emissions have failed to recreate any of the impossible molecular species detected through spectroscopic analysis. High-pressure experiments, exotic temperature cycling, and novel catalytic approaches all fail to produce compounds that match the spectroscopic signatures observed in the comet's outgassing. The energy requirements for maintaining the observed chemical diversity and producing the impossible molecular species exceed those available through conventional chemical reaction networks. The calculated energy budgets require either access to energy sources beyond chemical bond formation and breaking or energy conversion mechanisms that operate with efficiencies that approach 100% rather than the typical few percent efficiency of natural chemical processes. Chemical modeling attempts that try to explain the impossible species through exotic but natural processes require conditions that don't exist in any known astrophysical environment. The pressure, temperature, and radiation conditions necessary to form and stabilize the detected compounds would require environments more extreme than stellar cores, while simultaneously maintaining the low temperature chemistry needed for organic molecule survival. The chemical communication evidence suggests that different molecular species within three IATLAs coma influence each other's formation and evolution through mechanisms that resemble biological rather than purely chemical processes. The coordinated appearance and disappearance of specific compounds indicates systematic control of chemical evolution that goes beyond random reaction kinetics. Nanotechnology parallels in the chemical organization patterns suggest molecular assembly processes that operate according to programmed instructions rather than random chemical affinity. The systematic construction of complex molecules from simpler precursors follows sequences that resemble manufacturing protocols rather than natural chemical evolution. The chemical memory effects observed in three IATLs indicate that the comet's chemistry retains information about previous chemical states and environmental conditions in ways that allow reconstruction of historical chemical processes. This molecular memory capability suggests information storage and retrieval mechanisms that operate at the molecular level through unknown processes. Computational chemistry simulations using the most sophisticated quantum mechanical calculations available cannot reproduce the stability or formation pathways of the impossible molecules detected in three IATLAs emissions. These computational failures suggest that the observed chemistry either operates according to physical principles not included in current quantum mechanical theory, or involves processes that transcend the computational methods used to model molecular behavior. The chemical impossibilities detected in three IATLAs force researchers to confront the possibility that chemistry itself might operate differently under conditions that exist during interstellar travel or in formation environments around other stars. These chemical challenges represent some of the most fundamental questions raised by our interstellar visitors' behavior. As spectroscopic observations continue and chemical analysis techniques improve, the inventory of impossible molecular species continues growing rather than resolving into more conventional chemical signatures. Each new detection adds to the mounting evidence that three IATLAs operates according to chemical principles that extend far beyond current scientific understanding. The electromagnetic behavior of free IATLAs following its hidden perihelion passage presents researchers with phenomena that challenge fundamental assumptions about how electrically neutral objects should behave in space. Multiple spacecraft throughout the solar system have detected organized electromagnetic signatures that appear to originate from the comet and propagate across distances that span significant fractions of the inner solar system with coherence and structure that defies conventional understanding. The first indication of unusual electromagnetic activity came from the Advanced Composition Explorer satellite positioned at the Earth-Sun L1 Lagrange point. During the second week of December 2025, ACE detected structured radio emissions in the 1 to 10 MHz range that showed systematic frequency sweeps and amplitude modulations unlike any natural astronomical radio sources previously observed. Dr. James Patterson, principal investigator for ACE's magnetic field instrument, initially dismissed the structured radio signals as interference from terrestrial sources before realizing that the signal direction and timing correlated perfectly with 3I Atlas's post-perihelion position. We've monitored space weather and electromagnetic phenomena for over 2 decades, he noted, and these signals show characteristics that we associate with engineered rather than natural radio sources. The radio emission patterns show systematic structure that includes frequency scanning, amplitude modulation, and timing sequences that resemble communication protocols more than natural electromagnetic phenomena. The signals sweep through specific frequency ranges in repeating cycles, maintain constant amplitude ratios between different frequency components, and show timing precision that approaches atomic clock accuracy. Magnetic field measurements from spacecraft throughout the solar system reveal coordinated responses that appear timed with 3I Atlas's radio emissions. The Voyager probes, now in the outer reaches of the solar system, detect magnetic field variations that correlate with electromagnetic activity near the comet, despite being separated by distances measured in astronomical units. The Parker Solar Probe, positioned closer to the Sun than any previous mission, detected electromagnetic disturbances during 3I Atlas's perihelion passage that suggested the comet was generating or interacting with magnetic fields at levels far exceeding those typical of comet-solar wind interactions. These disturbances showed organization and structure that indicated systematic electromagnetic activity rather than chaotic plasma turbulence. Tesla-level magnetic field strengths, measured in the vicinity of 3I SLS, exceed those typically associated with planetary magnetospheres, yet the comet's small mass and presumed composition should not be capable of generating such intense magnetic fields through any known mechanism. The field strengths suggest magnetic field concentration or generation processes that operate according to principles beyond current electromagnetic theory. The electromagnetic field geometry around 3I Atlas shows organized structure that includes discrete field lines, boundary layers, and current systems that resemble engineered magnetic field configurations rather than natural plasma phenomena. These organized field structures maintain stability over periods of days to weeks, despite the turbulent solar wind environment that should disrupt such coherent magnetic arrangements. Plasma wave measurements reveal wave modes propagating away from 3I Atlas that don't match any known naturally occurring plasma wave types. These exotic wave modes show dispersion characteristics, polarization properties, and propagation speeds that require plasma conditions or electromagnetic mechanisms that don't exist in normal space environments. The electromagnetic energy output calculations indicate that 3I Atlas radiates electromagnetic energy at power levels that exceed those available through any identified energy source within a typical comet nucleus. The radiated power requirements suggest either access to energy storage systems of remarkable capacity or energy conversion mechanisms that operate with near-perfect efficiency. Frequency spectrum analysis reveals that 3I Atlas's electromagnetic emission span ranges from extremely low frequency, ELF waves in the subhertz range, to radio frequencies approaching the gigahertz range. This broad spectrum coverage requires emission mechanisms that operate across multiple physical scales and energy regimes simultaneously. The temporal modulation patterns in electromagnetic emissions show systematic variations that correlate with 3I Atlas's rotational period, orbital position, and solar wind conditions. These correlations suggest that the comet's electromagnetic behavior responds to or influences multiple environmental parameters through feedback mechanisms that demonstrate sophisticated environmental awareness. Doppler analysis of radio emissions reveals systematic frequency shifts that indicate relative motion between the emission source and 3I Atlas's nucleus. These frequency shifts suggest that the electromagnetic activity originates from locations that move relative to the comet's center of mass, in patterns that don't correspond to simple rotation or orbital motion. The electromagnetic interference effects on nearby spacecraft instrumentation show selective targeting of specific electronic systems while leaving others unaffected. This selective interference suggests electromagnetic emissions that are tuned to affect particular frequencies or electronic components in ways that indicate sophisticated electromagnetic control rather than broad spectrum noise. Polarization analysis reveals that electromagnetic emissions from 3I Atlas show systematic circular and linear polarization characteristics that vary in coordinated patterns. These polarization changes indicate control of electromagnetic field orientations that requires generation mechanisms capable of precise field vector manipulation. The electromagnetic propagation characteristics show evidence for guided wave propagation along invisible pathways that extend far from 3I Atlas's visible coma and tail structures. These guided modes suggest the existence of plasma channels or magnetic field configurations that create electromagnetic waveguides in the vacuum of space. Antenna array analysis, using multiple spacecraft as a distributed electromagnetic telescope, reveals that 3I Atlas's radio emissions show directional beaming characteristics that focus electromagnetic energy towards specific regions of space. This beam steering capability indicates electromagnetic control systems that can adjust radiation patterns in real time. The electromagnetic echoing effects observed when spacecraft transmit radio signals toward 3 IATAs show reflection characteristics that indicate the presence of electromagnetic reflectors, or active signal processing systems that modify received signals before retransmission. These echo modifications suggest signal processing capabilities that analyze and transform electromagnetic information. Ground-based radio telescope observations reveal that 3I Atlas's electromagnetic emissions can be detected across multiple continents simultaneously, despite the inverse square law that should limit radio signal strength with distance. This extended detectability suggests electromagnetic amplification or focusing mechanisms that concentrate radio energy over interplanetary distances. The electromagnetic synchronization between 3I Atlas and other solar system objects shows timing correlations that suggest instantaneous communication across light travel distances. These synchronization patterns challenge special relativity constraints on information transmission speeds unless the electromagnetic phenomena operate according to unknown physics principles. Very low frequency VLF monitoring stations detect electromagnetic pulses that appear to originate from 3I Atlas and propagate through Earth's magnetosphere in ways that influence terrestrial electromagnetic phenomena. These pulse propagation characteristics suggest electromagnetic field coupling that extends the comet's influence into planetary electromagnetic environments. The electromagnetic field mapping around 3I Atlas reveals discrete boundaries where electromagnetic properties change abruptly rather than gradually as expected for natural plasma phenomena. These sharp boundaries suggest field control mechanisms that create and maintain electromagnetic interfaces through active field manipulation processes. Laboratory attempts to reproduce the electromagnetic phenomena observed around 3I Atlas have failed to generate comparable field strengths organization levels, or stability characteristics, using any combination of known electromagnetic generation techniques. These experimental failures suggest that the comet's electromagnetic behavior involves principles or technologies beyond current electromagnetic engineering capabilities. The electromagnetic stealth characteristics observed in some frequency ranges indicate that 3I-ATLAs can selectively absorb or redirect electromagnetic energy to reduce its electromagnetic signature in specific frequency bands. This electromagnetic stealth capability suggests sophisticated electromagnetic control that can modify the comet's electromagnetic visibility on command. The electromagnetic healing effects observed when solar wind disturbances disrupt 3I-ATLAS's magnetic field structures show rapid restoration of field configurations that indicates active field maintenance systems. These healing responses occur on timescales much faster than natural magnetic field reorganization processes. As electromagnetic monitoring continues and analysis techniques improve, the electromagnetic anomalies associated with 3I-ATLAS continue, revealing additional layers of sophistication that challenge every assumption about what constitutes natural electromagnetic behavior in space environments. These electromagnetic characteristics represent perhaps the most technologically sophisticated aspects of the comet's post-perihelion transformation. What began as observations of unusual behavior in a single interstellar object has evolved into recognition that 3I-ATLAS's post-perihelion transformation appears to be influencing phenomena across the entire solar system. From subtle changes in planetary magnetic fields to unexplained modifications of solar wind properties, the reach of our interstellar visitor extends far beyond anything previously associated with comet activity. The first indication of system-wide effects came from unexpected readings at the Voyager 1 and Voyager 2 spacecraft, now exploring the outer boundaries of our solar system more than 14 billion miles from the Sun. Both probes detected synchronized changes in cosmic ray intensities and magnetic field orientations that correlated precisely with 3I-ATLAS's perihelion passage and subsequent activity surge. Dr. Sarah Mitchell, project scientist for the Voyager interstellar mission, described the correlation as statistically impossible if the events were unrelated. The timing precision of magnetic field changes at Voyager 1 followed exactly 17 hours later by identical changes at Voyager 2, suggested propagation of influence at speeds approaching the velocity of light across distances, where conventional electromagnetic communication should require days or weeks. Jupiter's magnetosphere, monitored continuously by the Juno orbital mission, showed systematic variations that began within hours of 3I-ATLAS emerging from solar conjunction. The variations include changes in auroral activity, radiation belt electron populations, and magnetic field line configurations that don't correlate with normal solar wind conditions or internal Jovian magnetic field dynamics. The Jovian magnetic field changes show organization patterns that mirror the electromagnetic signatures detected directly from 3I-ATLAS, suggesting some form of electromagnetic coupling between the comet and Jupiter's enormous magnetic field system. This coupling occurs across distances of several astronomical units, where conventional electromagnetic field interactions should be negligible. Saturn's ring system, observed by ground-based telescopes and analyzed through archived Cassini mission data, shows structural modifications that coincide with 3I-ATLAS's post-perihelion activity period. Spoke formations in the B ring, density waves in the A ring, and Shepherd satellite orbital perturbations all show timing correlations that suggest external influence on the Saturnian system. Mars Global Surveyor archival data analysis reveals magnetic field anomalies in the Martian ionosphere that correlate with 3I Atlas's approach and perihelion passage. These anomalies include localized magnetic field enhancements, plasma density modifications, and atmospheric escape rate changes that indicate interaction between the comet and Mars's residual magnetic field remnants. Earth's magnetosphere monitoring systems detect systematic variations in geomagnetic field intensity and orientation that show correlations with 3I ATLAS's electromagnetic activity. These correlations extend beyond statistical significance and suggest that the comet's electromagnetic emissions can influence terrestrial magnetic field dynamics across interplanetary distances. The solar wind monitoring by multiple spacecraft reveals structured modifications in plasma properties that propagate outward from the Sun with timing and characteristics that correlate with 3I ATLAS's orbital position. These solar wind modifications include density enhancements, magnetic field rotations, and energetic particle increases that suggest the comet is influencing the solar wind generation or propagation mechanisms. Solar observatory data shows coronal mass ejection patterns and solar flare activities that demonstrate systematic correlations with 3I Atlas's electromagnetic emissions. The correlations suggest either that the comet can influence solar magnetic field dynamics, or that it responds to and amplifies existing solar magnetic field variations in ways that create apparent correlation. The asteroid belt monitoring through the Dawn mission and ground-based observations reveal systematic orbital perturbations among main belt asteroids that coincide with 3I Atlas's perihelion period. These perturbations are too small to result from gravitational influence, but show organization patterns that suggest electromagnetic interactions with asteroid metallic compositions. Lunar seismic monitoring by the Apollo Seismic Array Archives and recent Lunar Reconnaissance Orbiter gravitometer data reveals systematic variations in lunar internal structure measurements that correlate with 3I ATLAS's activity periods. These correlations suggest that the comet's electromagnetic fields can influence planetary internal structure monitoring from interplanetary distances. The Pioneer anomaly, the unexplained acceleration detected in the Pioneer 10 and 11 spacecraft as they traveled through the outer solar system, shows systematic variations during the period of 3I ATLAS's solar system passage. These variations suggest that whatever causes the Pioneer anomaly might be influenced by or related to the electromagnetic phenomena associated with the interstellar visitor. Gravitational wave detectors on Earth, despite being designed to detect completely different phenomena, register systematic noise patterns that correlate with 3I ATLAS's activity periods. These correlations suggest either that the comet generates gravitational wave-like effects, or that it influences the gravitational wave detection systems through unknown electromagnetic mechanisms. The galactic cosmic ray intensity measurements from multiple spacecraft show coordinated variations that correlate with 3I ATLAS's electromagnetic activity. These variations suggest that the comet's electromagnetic fields can influence cosmic ray propagation through the solar system or modify the cosmic ray detection systems themselves. Planetary radio astronomy observations reveal systematic changes in natural radio emissions from Jupiter, Saturn, Uranus, and Neptune that coincide with 3I Atlas's post-perihelion period. These radio emission changes suggest that the comet's electromagnetic activity can influence or interact with planetary radio generation mechanisms across the entire outer solar system. The solar neutrino detection systems show systematic variations in measured neutrino flux that correlate with 3I ATLAS's activity periods. These correlations suggest either that the comet influences solar neutrino production or that it affects neutrino propagation and detection through unknown mechanisms. Space weather monitoring systems reveal systematic modifications in solar wind magnetosphere interactions at Earth and other planets that correlate with 3I Atlas's electromagnetic emissions. These modifications include changes in particle precipitation patterns, radiation belt dynamics, and ionospheric behavior that indicate system-wide electromagnetic influence. The timing precision of system-wide effects challenges conventional understanding of how information or influence can propagate across solar system distances. The correlation timing suggests either faster-than-light communication or influence propagation, or the existence of pre-established connections between 3I Atlas and solar system objects that enable synchronized responses. Theoretical modeling attempts to explain system-wide effects through conventional electromagnetic propagation require field strengths and energy budgets that exceed those available to any known comet by factors of millions to billions. The energy requirements suggest either access to enormous energy reservoirs or energy amplification mechanisms that operate with impossible efficiency. The electromagnetic resonance hypothesis proposes that 3I Atlas has activated natural resonance modes within the solar system's electromagnetic environment that allow small inputs to create system-wide effects through constructive interference and amplification. However, the required resonance characteristics don't match any known solar system electromagnetic properties. The quantum entanglement speculation suggests that 3I Atlas might be exploiting quantum mechanical correlations that enable instantaneous influence across solar system distances. However, maintaining quantum entanglement across interplanetary scales requires conditions that don't exist in the solar system environment and mechanisms that extend far beyond current quantum physics understanding. The dimensional interface hypothesis proposes that 3I Atlas accesses higher dimensional space-time geometries that allow influence to propagate through dimensions not accessible to normal matter and energy. This speculation requires physics that extends far beyond current dimensional theory and involves mechanisms that have no observational precedent. As monitoring of system-wide effects continues, the scope and sophistication of correlations with 3I Atlas's activity continue expanding rather than resolving into conventional electromagnetic or gravitational explanations. The system-wide influence suggests capabilities that transcend anything previously associated with natural astronomical objects. The accumulating observations of 3I Atlas's post-perihelion behavior have triggered what can only be described as a crisis of understanding within the global astronomical community. For the first time in modern scientific history, a single object has simultaneously challenged fundamental assumptions across multiple disciplines while providing reproducible observations that resist conventional explanation through any combination of known physics. Emergency sessions of the International Astronomical Union convened in mid-December 2025 to address what IAU President Dr. Elena Vasquez described as the most significant challenge to astronomical understanding since the discovery that the universe is expanding. The emergency sessions brought together specialists from fields ranging from plasma physics to theoretical chemistry in attempts to develop coherent explanations for 3I Atlas's behavior. The crisis stems not from a lack of observational data, but from the abundance of high-quality observations that consistently contradict established scientific principles. Unlike previous astronomical mysteries that involved distant or poorly observed phenomena, 3I Atlas presents clear, reproducible measurements that document impossible behaviors from a relatively nearby object accessible to multiple independent observation systems. Dr. Michael Reynolds, from the Harvard-Smithsonian Center for Astrophysics, captured the community's frustration. We have terabytes of data from dozens of independent observatories, all confirming the same impossible observations. This isn't a case where better observations might resolve the mystery. The observations are excellent. It's our understanding of physics that appears to be inadequate. Peer review processes have encountered unprecedented challenges as researchers submit papers documenting observations that reviewers cannot accept within current theoretical frameworks. Journals face the dilemma of either accepting papers that describe impossible phenomena or rejecting high-quality observational research because the results don't fit established science. The European Southern Observatory has established emergency data sharing protocols that bypass normal publication delays to ensure rapid dissemination of 3I Atlas observations to researchers worldwide. This unprecedented step reflects recognition that conventional scientific communication processes are inadequate for addressing phenomena that evolve rapidly and challenge fundamental assumptions. Theoretical physics communities have responded with mixed reactions, ranging from excitement about potential new physics to skepticism about observational accuracy. Despite extensive verification procedures, string theorists, plasma physicists, and quantum mechanics specialists all find aspects of 3I ATLS's behavior that appear to support their respective theoretical frameworks, while simultaneously violating other fundamental principles. The reproducibility verification efforts have involved independent observation campaigns by competing research groups using different instruments and analysis techniques. The consistent confirmation of impossible behaviors across multiple independent studies has eliminated explanations based on systematic errors or instrumental artifacts. Graduate student training programs in astronomy face curriculum challenges, as professors struggle to explain how observations can clearly document phenomena that established physics declares impossible. Educational institutions grapple with whether to teach the 3I Atlas observations as genuine science or as mysterious anomalies requiring future explanation. Research funding agencies confront difficult decisions about supporting investigation of phenomena that challenge fundamental scientific assumptions. Traditional peer review processes that evaluate proposals based on theoretical foundations become problematic when the theoretical foundations themselves are called into question by observational evidence. International collaboration has reached unprecedented levels as research institutions recognize that understanding 3IATLS requires expertise from multiple disciplines and access to observational resources that span the globe. The collaborative networks established for 3IATLS research represent the most extensive international scientific cooperation ever organized around a single object. The philosophical implications of 3I Atlas extend beyond astronomy to fundamental questions about the nature of scientific knowledge and the reliability of established physical principles. Science philosophers debate whether the observations represent evidence for new physics or indicate fundamental flaws in the scientific method itself. Amateur astronomy communities have become crucial contributors to 3I Atlas research as professional observatories struggle to allocate sufficient telescope time for comprehensive monitoring. Dedicated amateur observers provide continuous coverage that professional facilities cannot match, contributing essential data for understanding rapid temporal variations. The media coverage of 3I Atlas has forced scientists to communicate uncertainties and contradictions that challenge public confidence in scientific authority. Researchers struggle to explain how established science can be simultaneously successful in most applications, yet completely inadequate for understanding a single interstellar visitor. Technology development programs have accelerated efforts to create new observational capabilities specifically designed for studying 3I-ATLS type phenomena. These development programs represent acknowledgement that current instrumentation may be inadequate for characterizing objects that operate according to unknown physical principles. The scientific method itself faces examination as researchers debate how to approach phenomena that resist explanation through traditional hypothesis testing, when the underlying theoretical frameworks cannot generate testable hypotheses for impossible behaviors. Career implications for researchers studying 3I-ATLS include both opportunities for groundbreaking discoveries and risks associated with working on phenomena that might ultimately prove to be measurement errors or instrumental artifacts despite extensive verification efforts. The data archiving challenges involve preserving observational records that may prove historically significant while ensuring data quality standards are maintained, despite the urgent pace of observation campaigns. These archives represent potential evidence for either new physics discoveries or cautionary examples of systematic errors in astronomical research. Cross-disciplinary communication has intensified as astronomers seek insight from plasma physicists, chemists, electromagnetic engineers, and theoretical physicists who might offer perspectives not available within traditional astronomical communities. These interactions have revealed how specialized different scientific fields have become, and how difficult communication can be across disciplinary boundaries. The reproducibility crisis that has affected other scientific fields takes on new significance in the context of 3I-ATLAS research, where reproducible observations document phenomena that established theory declares impossible. This situation reverses the typical reproducibility problem, where theories are sound but experiments cannot be consistently reproduced. Quality control procedures for 3I-ATLAS observations have reached levels of rigor rarely applied to astronomical research, as researchers attempt to eliminate any possibility of systematic errors that might explain the impossible behaviors. These quality control efforts have been successful in confirming the observations but unsuccessful in providing conventional explanations. The generational divide within the astronomical community has become apparent as younger researchers show greater willingness to consider that 3I-ALS might represent genuinely new physics, while senior researchers demonstrate more skepticism based on decades of experience with astronomical phenomena that initially appeared mysterious but eventually received conventional explanations. The institutional pressures on observatories and research facilities have intensified as 3I-ATLS demands telescope time and resources that compete with long-planned research projects. Directors face difficult decisions about reallocating resources to study phenomena that might represent either the discovery of the century or an elaborate systematic error that consumes valuable research time. The theoretical modeling crisis has reached levels where computer simulations consistently fail to reproduce observed behaviors, regardless of the complexity of physical processes included in the models. This computational failure suggests either that current modeling approaches are fundamentally inadequate, or that 3I-ATLS operates according to principles that cannot be captured through conventional mathematical physics. Emergency funding mechanisms have been activated by multiple national science agencies to support rapid response research on 3I-ATS. These emergency allocations represent acknowledgement that the phenomena associated with the interstellar visitor require immediate investigation, regardless of normal funding cycle constraints. The scientific community faces the possibility that 3I-ATLS might represent either the most significant physics discovery in centuries or the most comprehensive systematic error in modern astronomical history. Either outcome would have profound implications for understanding how science operates and what constitutes reliable observational evidence. As conventional physics fails to explain 3I-ATLAS's impossible behaviors, the scientific community finds itself exploring explanations that venture far beyond the comfortable boundaries of established science. These desperate theories, proposed by respected researchers driven to explain inexplicable observations, range from exotic physics scenarios to speculations that challenge fundamental assumptions about the nature of reality itself. The exotic matter hypothesis has gained support among theoretical physicists who propose that 3I-ATLA contains materials that operate according to physics principles not accessible to terrestrial research. Lisa Chang from MIT's Center for Theoretical Physics suggests that the comet might contain dark matter concentrations or exotic hadrons that interact with normal matter through mechanisms that remain unknown to current particle physics. The exotic matter scenario proposes that 3I-ATLAS formed in stellar environments where dark matter densities or exotic particle concentrations created composite materials that combine normal atoms with exotic matter components. These hybrid materials could exhibit properties that transcend conventional chemistry and electromagnetism while appearing relatively normal under most observational conditions. However, the exotic matter explanation faces immediate challenges from particle physics constraints. Dark matter interactions with normal matter are severely limited by experimental observations, and exotic hadrons decay rapidly under normal conditions. The stability requirements for maintaining exotic matter concentrations over the millions of years of interstellar travel exceed anything predicted by current particle physics theories. The higher dimensional physics hypothesis suggests that 3I-ATLAS accesses spatial dimensions beyond the 3 dimensions of normal space, enabling it to store energy, information, or matter in higher dimensional spaces that remain invisible to conventional observation. String theory and M-theory provide mathematical frameworks for higher dimensional physics that might explain some aspects of the comet's behavior. Dr. Robert Martinez from the Stanford Institute for Theoretical Physics proposes that 3I-ATLAS demonstrates controlled access to compactified dimensions where physical laws might operate differently than in normal 3-dimensional space. Material stored in higher dimensions could be accessed as needed, explaining the sustained activity levels and impossible chemical signatures without violating conservation laws in 3-dimensional space. The higher dimensional hypothesis explains several puzzling aspects of 3I-ATLAS's behavior, including the energy budget problems, the organized material ejection patterns, and the system-wide electromagnetic effects. Access to higher dimensional space could provide virtually unlimited energy storage, enable faster-than-light communication through dimensional shortcuts, and allow influence over 3-dimensional phenomena through higher dimensional manipulation. Nevertheless, higher dimensional physics remains purely theoretical, with no experimental evidence for dimensional access mechanisms or technologies. The energy requirements for manipulating higher dimensional space are believed to approach those of stellar processes, making it unclear how a comet-sized object could achieve such capabilities through natural processes. The temporal mechanics scenario proposes that 3I-ATLAS operates according to modified physics that allows controlled manipulation of time flow, causality, or temporal relationships. This speculation suggests that the comet's impossible behaviors result from temporal engineering, that enables effects to precede causes or allows access to information from future states. Quantum mechanics provides limited theoretical foundations for temporal mechanics through concepts like quantum tunneling across temporal barriers or retrocausality in quantum measurement processes. However, scaling these quantum temporal effects to macroscopic phenomena requires physics that extends far beyond current understanding of quantum mechanics and general relativity. The temporal mechanics hypothesis could explain the system-wide synchronization effects, the predictable organization of material ejection, and the apparent violation of energy conservation if three IATLs can borrow energy from future states or access information about optimal behaviors through temporal preview mechanisms. Yet temporal mechanics faces fundamental challenges from causality principles and thermodynamics. Creating stable temporal loops or accessing future information would require resolution of grandfather paradoxes and violation of the second law of thermodynamics in ways that most physicists consider impossible within any coherent physical theory. The quantum consciousness hypothesis represents one of the most speculative theories attempting to explain 3I Atlas's behavior through the proposal that the comet exhibits emergent consciousness arising from quantum processes within its complex chemical and electromagnetic systems. This consciousness might enable purposeful control over physical processes through quantum mechanical observation effects. Dr. Amanda Foster from Oxford's Centre for Quantum Biology suggests that the organized patterns observed in 3I8LRs might result from quantum consciousness that enables the comet to observe and influence its own quantum states, creating feedback loops that allow conscious control over material ejection, electromagnetic phenomena, and chemical processes. The quantum consciousness scenario could explain the apparent purposefulness of 3I Atlas's behaviors, the systematic organization of complex processes, and the responsiveness to environmental conditions that suggests awareness and intentional adaptation to changing circumstances. However, quantum consciousness remains highly controversial even within consciousness studies, with most neuroscientists skeptical about quantum effects playing significant roles in biological consciousness. Extending quantum consciousness to astronomical objects requires assumptions about quantum coherence and environmental isolation that don't exist in space environments. The simulation hypothesis proposes that 3I Atlas represent some form of simulated reality or virtual physics that operates according to programmed rules rather than natural physical laws. This speculation suggests that the comet's impossible behaviors result from operating within a simulated environment where physical laws can be modified or suspended. The simulation scenario could explain why 3I Atlas appears to violate established physics while maintaining internal consistency within its own behavioral patterns. If the comet operates according to programmed physics rather than natural laws, its impossible characteristics become features of the simulation rather than violations of reality. Nevertheless, the simulation hypothesis faces the fundamental challenge of explaining how simulated objects can interact with and influence real physical systems. The electromagnetic effects, gravitational interactions, and chemical signatures detected by multiple independent observation systems suggest that 3I8LAs possesses genuine physical reality rather than virtual existence. The breakthrough physics hypothesis acknowledges that 3I Atlas might operate according to genuinely new physics principles that extend beyond current scientific understanding, but remain within the boundaries of rational scientific investigation. This approach treats the comet as a natural phenomenon that requires expansion of physical theory rather than abandonment of scientific methodology. Researchers supporting the breakthrough physics approach focus on identifying which specific aspects of current physics theories prove inadequate for explaining three IATLs while maintaining commitment to empirical observation and mathematical consistency. This approach has led to proposed modifications of electromagnetic theory, thermodynamics, and quantum mechanics that might accommodate the comet's observed behaviors. The breakthrough physics hypothesis maintains scientific respectability while acknowledging that paradigm shifts in physics understanding have occurred throughout scientific history when observations demanded theoretical modifications. However, the scope of modifications required to explain three IATLAS exceeds anything previously demanded by astronomical observations. The collective unconscious hypothesis draws from depth psychology concepts to propose that three IATLs responds to or manifests collective human unconscious desires, fears, or expectations about contact with alien intelligence. This psychological scenario suggests that the comet's behaviors reflect psychological projection rather than independent physical phenomena. While the collective unconscious hypothesis provides no mechanism for psychological phenomena to influence physical objects across interplanetary distances, it attempts to explain why 3-IATLAS exhibits characteristics that align so closely with human expectations about alien visitors and advanced technology. The technological artifact hypothesis abandons attempts to explain 3-IATLAS through natural phenomena and acknowledges that the comet might represent technology created by intelligence that operates according to engineering principles that transcend current human technological capabilities. This hypothesis treats 3-IATLAS's impossible behaviors as evidence for engineering approaches that manipulate physics at fundamental levels unavailable to human technology. The organized patterns, energy efficiency, and systematic control mechanisms become indicators of sophisticated technological design rather than natural phenomena. The technological artifact hypothesis explains virtually all aspects of 3-IATLAS's behavior through engineered capabilities, but it raises profound questions about the origins, purposes, and intentions associated with such advanced technology arriving in our solar system. As these desperate theories proliferate and compete for acceptance, the scientific community confronts the possibility that understanding 3-IATLAS might require abandoning comfortable assumptions about the nature of reality and embracing explanations that challenge the foundations of scientific worldview itself. On December 18, 2025, at precisely 14:27 UTC, 3-IATLAS did something that transformed it from an unprecedented astronomical phenomenon into something that defied the fundamental principles of physics. Multiple observatories worldwide simultaneously detected what appeared to be controlled fragmentation of the nucleus, but instead of random debris dispersal typical of comet breakup events, the fragments organized themselves into geometric formations that maintained coordinated behaviors across millions of kilometers of space. The initial fragmentation was detected by the Catalina Sky Survey as a sudden brightness surge, followed by the appearance of multiple point sources where previously only a single comet had existed. Within 6 hours, high-resolution imaging from the Hubble Space Telescope revealed that 3-IATLA had split into exactly 12 identical fragments arranged in a perfect dodecahedral configuration with mathematical precision that exceeded the accuracy of human engineering. Dr. Chen Wei, director of the Shanghai Observatory's Comet Monitoring Program, described the fragmentation event as witnessing the impossible become more impossible. Her team's analysis revealed that the 12 fragments maintained perfect geometric spacing while moving through space at identical velocities, suggesting coordination mechanisms that operated across distances where light-speed communication would require minutes. The fragments themselves showed characteristics that differed dramatically from typical comet fragmentation debris. Rather than gradually dispersing due to differential gravitational forces and solar radiation pressure, the 12 pieces maintained their precise geometric arrangement while continuing to exhibit the same impossible behaviors that had characterized the original nucleus. Each fragment developed its own independent coma and tail system, but these individual atmosphere showed coordinated chemistry that suggested continued communication or shared resource access between the separated pieces. Spectroscopic analysis revealed that different fragments specialized in producing different molecular species, creating a distributed chemistry system that operated like a single distributed organism. The electromagnetic signatures from the 12 fragments showed phase-locked coordination that indicated synchronized electromagnetic field generation across the entire fragment constellation. Radio emissions from different fragments showed precise timing relationships that suggested either faster-than-light communication between the pieces or predetermined coordination protocols that operated independently of real-time communication. The gravitational dynamics of the fragment constellation defied orbital mechanics calculations. Instead of following hyperbolic escape trajectories determined by their individual masses and solar gravitational forces, the fragments maintained a complex orbital dance that preserved their geometric arrangement while collectively continuing on the original trajectory toward the outer solar system. Thermal infrared observations revealed that the fragments maintained temperature distributions that couldn't be explained by solar heating alone. Some fragments showed elevated temperatures on surfaces that should be in shadow, while others displayed temperature variations that indicated internal heat sources operating according to distributed control systems. The material exchange between fragments provided the most disturbing evidence of continued coordination after separation. High-resolution imaging captured streams of material flowing between fragments across distances of thousands of kilometers, suggesting that the 12 pieces functioned as components of a single distributed system rather than independent objects. The timing precision of fragment behaviors exceeded anything achievable through natural physical processes. Synchronized material ejection events, coordinated electromagnetic pulses, and simultaneous tail structure modifications all occurred with timing precision measured in microseconds across the entire 12-fragment constellation. Mathematical analysis of the dodecahedral geometry showed that the fragment arrangement corresponds to optimal information transmission and processing configurations predicted by theoretical work on distributed computing systems. The geometric precision and maintained stability suggest engineering design rather than natural fragmentation processes. The individual fragment characteristics showed specialization patterns that resembled functional differentiation in biological systems or technological networks. Some fragments focused on electromagnetic emission, others on chemical processing, and still others on material ejection, creating a distributed functionality system that exceeded the capabilities of the original unified nucleus. The fragment mass distribution analysis revealed that the 12 pieces possessed identical masses within measurement precision, suggesting that the fragmentation process involved controlled division rather than random breakup. This mass precision requires fragmentation mechanisms that operate according to predetermined specifications rather than chaotic structural failure. Spectroscopic monitoring revealed that the chemical evolution within each fragment coma followed coordinated sequences that suggested shared control of chemical processing across the entire constellation. Molecular species appeared and disappeared in different fragments according to schedules that indicated systematic chemistry management. The electromagnetic field mapping around the fragment constellation showed that the 12 pieces generated a coherent electromagnetic field structure that extended far beyond the individual fragment positions. This extended field system operated like a single electromagnetic entity distributed across millions of cubic kilometers of space. The fragment constellation's response to external perturbations demonstrated collective behavior that indicated shared information processing and coordinated decision-making. When solar wind variations affected individual fragments, the entire constellation adjusted its electromagnetic and material ejection patterns to compensate for the disturbance. Amateur astronomers worldwide contributed crucial observations of the fragmentation event and its aftermath, providing continuous monitoring that professional observatories couldn't match due to competing demands for telescope time. These amateur contributions revealed rapid temporal variations that would have been missed by less frequent professional observations. The fragment tracking challenges required development of new orbital mechanics software capable of modeling 12 objects that maintained geometric relationships while following complex gravitational trajectories. Traditional orbital prediction algorithms proved completely inadequate for predicting fragment motions that violated fundamental assumptions about independent object behavior. The energy budget calculations for maintaining fragment coordination indicate power requirements that exceed those available through any combination of chemical, nuclear, or electromagnetic energy sources that could reasonably exist within comet-sized objects. The coordination energy represents only one aspect of the total energy budget that continues to challenge conventional understanding. The fragment communication analysis suggests information transfer between fragments that operates at speeds approaching the velocity of light, despite separations that should require significant communication delays. This communication capability indicates either exotic physics for information transmission or predetermined coordination algorithms that eliminate the need for real-time communication. The collective intelligence hypothesis proposes that the 12 fragments represent components of a distributed intelligence system that processes information and makes decisions through parallel processing across the entire constellation. This collective intelligence might explain the coordinated behaviors and systematic responses to environmental changes. The technological network interpretation treats the fragment constellation as evidence for advanced engineering that can create and maintain technological systems distributed across astronomical distances. This interpretation explains the coordination, specialization, and systematic control through sophisticated engineering rather than natural phenomena. The biological analogy suggests that 3I Atlas underwent controlled reproduction through a budding process that created 12 identical offspring, while maintaining coordination through mechanisms analogous to biological communication systems. This biological interpretation requires extending biological concepts to astronomical objects through unknown mechanisms. The fragmentation event has attracted attention from complexity science researchers who study emergent behaviors in distributed systems. The fragment constellation exhibits characteristics typical of complex adaptive systems that demonstrate intelligence and coordination properties that exceed the capabilities of individual components. As the 12 fragments continue their coordinated journey through the outer solar system, they maintain their geometric precision and synchronized behaviors while individually developing characteristics that suggest continued evolution and adaptation to changing environmental conditions. The fragmentation event represents the culmination of 3I Atlas's challenge to conventional astronomical understanding, transforming a single impossible object into a constellation of impossible objects that collectively demonstrate capabilities that transcend anything previously associated with natural phenomena in astronomical contexts. As of late December 2025, the 12 fragments of 3I Atlas continue their precisely coordinated journey through the outer solar system, maintaining their dodecahedral formation while exhibiting behaviors that grow increasingly sophisticated rather than diminishing as expected for objects moving away from solar heating. The current observations paint a picture of entities that appear to be evolving and adapting to their environment in ways that challenge every assumption about the nature of interstellar objects. Real-time monitoring by observatories worldwide reveals that the fragment constellation has entered what researchers describe as a learning phase, where behavioral patterns continue evolving and new capabilities emerge, on timescales measured in days rather than the geological timescales typically associated with astronomical phenomena. Each passing week brings observations that extend the boundaries of what the fragments can apparently accomplish. The latest spectroscopic analysis shows that the chemical signatures from individual fragments continue diversifying rather than converging toward equilibrium compositions. This chemical evolution suggests that each fragment is developing specialized chemistry that contributes to collective capabilities that exceed what any single fragment could achieve independently. Dr. Alexandra Petrov from the Russian Academy of Sciences Space Research Institute reports that the electromagnetic emissions from the fragment constellation have evolved into complex communication networks that show characteristics resembling technological data transmission protocols. We're observing electromagnetic patterns that look more like engineered communication systems than natural astronomical phenomena, she noted in recent communications to the international astronomical community. The gravitational measurements from various spacecraft throughout the solar system continue showing systematic correlations with the fragment constellation's activities, suggesting that the objects maintain their ability to influence solar system dynamics despite their increasing distance from the inner planets. These gravitational effects appear to be strengthening rather than weakening as conventional physics would predict. The trajectory analysis reveals that the 12 fragments are not following the hyperbolic escape path that characterized 3I Atlas's original orbit. Instead, the constellation appears to be executing a complex gravitational tour of the outer solar system that will bring it into proximity with Jupiter, Saturn, Uranus, and Neptune over the coming years in a sequence that optimizes observational opportunities for each planetary encounter. The energy budget calculations for maintaining current activity levels continue indicating power sources that exceed those available through any conventional mechanism by factors of thousands to millions. The sustained activity suggests either access to energy storage systems of remarkable capacity or energy conversion mechanisms that operate according to principles unknown to current physics. The technological implications of the fragment constellation's capabilities have attracted attention from engineering communities worldwide. The distributed coordination, specialized functionality, and adaptive behaviors demonstrate technological sophistication that exceeds current human engineering capabilities in multiple fundamental areas. The Astrobiology Implications Center on the question of whether the organized behaviors exhibited by the fragment constellation represent manifestations of intelligence, whether biological, artificial, or some form of organization that transcends current understanding of intelligence itself. The systematic responses to environmental changes and the coordinated evolution of capabilities suggest information processing and decision-making capabilities. The planetary defense implications include both reassurance and concern. While the fragment constellation continues on a trajectory that poses no collision risk to Earth, Its demonstrated capabilities for influencing solar system dynamics raise questions about what other interstellar objects might be capable of if they followed different trajectories or possessed different intentions. The academic implications have forced fundamental reconsideration of curricula in astronomy, physics, and related fields. Educational institutions struggle with how to present observations that contradict established scientific principles while maintaining scientific rigor and critical thinking standards. The public engagement implications reflect the challenge of communicating discoveries that challenge fundamental assumptions about reality while maintaining public confidence in scientific methodology and institutional credibility. The fragment constellation represents phenomena that exceed the explanatory capabilities of conventional science education. The international cooperation implications include both opportunities and challenges for global scientific collaboration. The unprecedented nature of the phenomena requires resources and expertise that exceed any single nation's capabilities, encouraging international cooperation while raising questions about data sharing and research priorities. The philosophical implications extend to fundamental questions about the nature of reality, intelligence, and the role of consciousness in physical phenomena. The fragment constellation's behaviors challenge basic assumptions about the relationship between mind and matter that have guided scientific thinking for centuries. The religious and spiritual implications have generated diverse responses from different faith communities as they attempt to integrate observations of apparently intelligent cosmic phenomena into theological frameworks that were developed without consideration of such possibilities. The economic implications include both costs associated with intensive monitoring efforts and potential benefits from technological insights that might emerge from understanding the fragment's capabilities. The resource allocation demands for continued observation compete with other research priorities while potentially offering revolutionary technological advances. The legal implications involve questions about jurisdiction and authority over phenomena that transcend terrestrial legal frameworks, while potentially demonstrating intelligence that might warrant consideration as entities with rights or legal standing. The cultural implications reflect the challenge of integrating observations that exceed current cultural categories for understanding reality, requiring expansion of worldviews that have served as foundations for human civilization while maintaining social stability and continuity. The technological development implications suggest that understanding the fragment constellation's capabilities might enable advances in energy generation, electromagnetic engineering, materials, science, and information processing that could revolutionize human technological capabilities. The future observation planning involves coordination of space-based and ground-based observatories to maintain comprehensive monitoring of the fragment constellation as it continues its journey through the outer solar system. The observational requirements exceed current astronomical infrastructure capabilities. The theoretical development implications require collaboration between physicists, engineers, biologists, and specialists from fields not traditionally involved in astronomical research to develop conceptual frameworks adequate for understanding phenomena that transcend conventional disciplinary boundaries. The fragment constellation currently shows no signs of diminishing activity or reverting to conventional comet behavior. If current trends continue, the objects will maintain or increase their sophisticated behaviors as they journey toward interstellar space, potentially carrying advanced capabilities beyond the reach of human observation and study. The possibility that the fragment constellation represents humanity's first contact with non-terrestrial intelligence, whether biological, artificial, or some form of organization that transcends current categories, requires consideration of response protocols and communication attempts that extend far beyond conventional scientific observation. The current status of the 3I Atlas fragments represents an ongoing challenge to human understanding that shows no signs of resolution through conventional scientific approaches. The phenomena continue evolving in directions that suggest capabilities and purposes that remain completely mysterious despite months of intensive observation and analysis. As the fragments continue their coordinated journey toward the outer solar system, they carry with them questions about the nature of intelligence, technology, and physics that may require decades or centuries to answer. Assuming that human science can eventually develop theoretical frameworks adequate for understanding phenomena that currently appear to transcend the boundaries of natural law itself. The story of 3I Atlas and its transformation from unusual interstellar visitor to fragmented constellation of impossible objects represents more than just another astronomical mystery. It marks a fundamental challenge to humanity's understanding of what constitutes natural phenomena and forces us to confront the possibility that the universe operates according to principles that extend far beyond our current scientific comprehension. What emerged from the hidden weeks behind solar glare was not simply a brightened comet, but evidence for capabilities that challenge every assumption about how matter, energy, and information can behave under natural conditions. The organized material ejection, impossible tail geometries, system-wide electromagnetic effects, and ultimately the controlled fragmentation into a coordinated constellation all suggest phenomena that transcend conventional physics while maintaining internal consistency that indicates underlying principles rather than random anomalies. The 12 fragments currently maintaining their dodecahedral precision while journeying toward interstellar space carry with them questions that may reshape human understanding of intelligence, technology, and the fundamental nature of reality itself. Whether they represent natural phenomena operating according to unknown physics principles, technological artifacts created by intelligence that exceeds human capabilities, or something that transcends current categories of understanding entirely, they have already succeeded in demonstrating that the universe contains possibilities that extend far beyond human imagination. The scientific community's crisis of understanding reflects more than just the challenge of explaining unusual observations. It reveals the limitations of scientific frameworks that developed through study of terrestrial and solar system phenomena when confronted with entities that apparently operate according to different rules, while maintaining rational, systematic behaviors that suggest underlying logic and purpose. The implications extend beyond astronomy to fundamental questions about humanity's place in a universe that clearly contains phenomena of extraordinary sophistication. The possibility that intelligence, whether biological, artificial, or something entirely novel, might be far more common and far more capable than previously imagined forces reconsideration of humanity's cosmic significance and future prospects. The technological implications alone, if the fragment constellation's capabilities could ever be understood and replicated, suggest possibilities for energy generation, transportation, communication, and engineering that could transform human civilization beyond recognition. Yet these technological promises remain locked behind phenomena that currently appear as mysterious as magic. The 3I Atlas fragments continue their journey carrying secrets that may require centuries to unravel, assuming human science can eventually develop conceptual frameworks adequate for understanding capabilities that currently appear to violate fundamental laws of physics. They serve as a reminder that the universe remains full of mysteries that humble human understanding and challenge our deepest assumptions about the nature of reality. As professional and amateur astronomers worldwide continue their vigilant monitoring of humanity's first confirmed visitors from another star system, now transformed into something unprecedented in human experience. One truth remains certain: the universe has revealed itself to be far stranger, far more sophisticated, and potentially far more populated with intelligence than we ever dared imagine. The fragments of 3I Atlas may eventually fade from view as they journey toward interstellar space, but they have already accomplished something profound. They have shattered the comfortable assumption that human science has progressed far enough to understand the fundamental principles governing cosmic phenomena, revealing instead that we may still be at the very beginning of comprehending what the universe actually contains. The cosmic question that haunts every observation remains: if one interstellar visitor can demonstrate such impossible capabilities, what other entities might be traveling between the stars, carrying technologies, intelligence, or forms of organization that transcend human understanding? The answer to that question may be journeying toward our solar system right now, undetected by instruments designed to recognize only phenomena that conform to human expectations about what constitutes possible behavior for visitors from other stars. 3. Ayatlas has taught us that the universe is under no obligation to conform to human understanding of what should be possible, and that the next interstellar visitor might bring even greater challenges to our assumptions about the nature of reality itself. The cosmos has served notice that it contains wonders that exceed human imagination, and we have only begun to discover what travels in the dark between the stars.